In the previous lecture, we had looked at the basic building blocks which are required to construct the processor design. We will now try to put these together to come up with a very simple design, and later on we will look at the performance issues and try to improve the design. So, what we will do today is have a simplest possible solution to the problem of taking a set of instructions and having a circuit execute those instructions. So, we will build this design in small steps, so that you can see each and every step clearly and get a clear picture of how the circuit is getting designed. So, we will start with a small set of instructions. First, we will take only R class instruction, which includes arithmetic, logical and comparison, add, subtract, and or, and SLT. So, that will be only part of the solution. Then we will add instruction by instruction and see how the whole thing can be built. So, with the basic skeleton of the design, we will include other instructions step by step. So, first we will include load store instructions to the basic set of 4-5 instructions, and then we will include the jump and branch instructions. So, after having put the data path together, we will try to see how you control it, what actually is required in terms of control signals to do it, make it do the right operation at the right time. And we will interconnect a controller to this data path which we will build. We will not go into detailed design of the controller, that will take up in the next class. So, once again let us look at the subset of the instructions which we have set out to consider for building this data path. Among the arithmetic and logical instructions, we have these 5: add, subtract, 2 arithmetic instructions and or 2 logical instructions, and SLT which does the comparison. So, they are all of same class in the sense that they take 2 operands from registers, perform some operation, put the result in register. Then we come to load and store, which access memory. Okay. So, basically the data is transferred between register file and memory one way or the other, and then instruction which influence the flow of control, BEQ which does a comparison and then decide which way to go, and jump which is an unconditional jump instruction. As I mentioned in the last class, the whole design will have 2 parts, the data path and the controller. The signals which go from controller to the data path are called control signals, and signals which come from data path to controller are considered as the status signal. So, controller times the activities in the data path and also directs what has to be done in which clock cycle or which instant. So, status signal is the information which controller seeks from the data path to decide its actions. Okay. So, we are going to begin with these 5 instructions: add, subtract, and or, and SLT. The process involved or the action which will be required would be to get the instruction from the memory, taking program counter contents as the address. Then depending upon the fields which contain register values, we access the register file. Okay. So, the register addresses will come from instruction fields, and the operand which we get from register file are passed on to ALU. Then the result produced by ALU is passed on to the register file, and we also increment the PC, make it ready for the next instruction. So, before we begin, let us look at the format of these instructions. The format has several fields. A 6-bit field is the opcode field, okay. And for all these instructions this is common. Okay. There is a single code which actually defines this a larger group than this. This is only a subset of all the instructions which have a common opcode here. Then there is a source register 5-bit, third register 5-bit. So, these 2 are the operands, these 2 specify addresses of the operands, and another 5-bit field specifies address of the destination. So, all these are numbers from 0 to 31, and specify one of the registers. Then this is unused. In some instructions this is used to specify shift amount, and it is this field which is called function field, which will distinguish these 5 instructions from one another and also from other instructions which are part of the group. So, we would need to look at all the fields except for this field, which is just to be ignored. So, the action begins by fetching an instruction from the program memory. So, we have program counter, a register which will carry the address of the current instruction, and there is an instruction memory. Okay. Instruction memory in this design will be assumed to be having fixed contents. We are not going to change the contents. So, the only input to this is an address input, okay, and the only output is an instruction which comes out of this. So, you give an address, instantly the instruction comes out, right. We assume that program is somehow stored in this memory already by some means. In fact, such memories are called read only memories, if you are familiar, okay, where by a special process you load the contents in the memory and then you can only access it, you can read it. So, in that sense this will behave like a combination circuit, does not require a clock. So, you give an input, you have an output, but the function which transforms the input to output is fixed, and by special processes it can be changed. So, PC feeds the address input of this memory and we get an instruction, all right. Next thing is to look at the instruction, various fields in the instruction, and address the register file. So, particularly for these 5 instructions we are talking of, we need to access RS and RT. So, which were the second and third field in the instruction, if you remember, and bits of this 32-bit instruction which we are getting would be used to address the register file. So, register file as I discussed yesterday. So, it specifically for this particular design we need a register file as an array of register with the provision of reading 2 values at a time. You can read 2 registers and you can write 1 register at any given time. So, now the addresses for these 3 things, 2 reading and 1 writing, are provided independently. They could be in general different, they 1, 2 or more can also coincide, but register file will respond correctly in all these cases. So, the 3 address inputs are read address 1, read address 2 and write address. Okay. These are the 3 inputs, each of these is 5 bits. There are 2 data outputs, read data 1 and read data 2, and there is 1 data input, write data. Okay. So, we have instruction which is 32 bits. So, specific fields are being tapped out of this. Okay. Bit number 21 to 25, this is RS, the source register, and that goes to 1 address. Bit number 16 to 20 form the field which defines RT or the third register. This goes and addresses RAD2 or second read address. Okay. So, the out of these 32 bits we are taking 2 groups of 5 bits and connecting it to register file. Okay. Now, once addresses are given, this register file will respond with data here, okay, and the operand which will come out of these will need to be passed on to the ALU. So, we have an ALU, imagine the same design which we did a couple of lectures back, where by specifying some control signal you could perform addition, subtraction, AND operation, OR operation, you could do comparison for equality, you could do comparison for less than, okay, for the purpose of SLT. So, same ALU we are putting now as a black box. Okay, we are not looking into details of what is inside, we understand that design and we are simply using it to build a larger circuit now. So, these 2 outputs are forming 2 inputs or 2 operands for the ALU, right. and next the result which is produced by ALU would be sent to register file for storage. Okay. And that's where the cycle of flow of data or cycle of this instruction would be complete. So, now at the moment I am not worrying about how to control ALU to do the right function. Now, we are looking at those 5 instructions together, and ALU would need to be told which of these instruction is. So, we will eventually, when we talk of control, we will look at bit number 26 to 31, the opcode field, and bit number 0 to 5, bit number 0 to 5, the function field. We look at those fields and then pass on some signals to ALU, so that it does the right operation. So, right now we are not distinguishing between those 5 and just looking at the overall flow of the data. So, output of ALU goes back to this register file to the write port. Okay. Let me just emphasize this terminology. These are called ports for the register file. Okay. Port means, there is something like gateways. So, there are 2 read ports in this and 1 write port, and this is going back to the write port. So, now when we are writing, we also need to arrange for the address where it has to be written. So, we need to look at another field from here and make sure that the address is also delivered correctly to the register file. So, bit number 11 to 15 are the destination address. Okay. And that connects to the third address input. So, now with this the cycle is complete. So, basically starting with PC, we have a sequential element here. Okay. So, at edge of a clock, a new value is available at the output of PC, okay, which defines address of a new instruction, and as a function of that we get the instruction, as a function of that we get the operand, as a function of that we get the result, and finally result is available at the input of register file. So, now at this point when a clock edge comes to register file, this information will get stored at that instant. So, we are assuming that transition in the state of register file would be edge triggered. So, you have one clock at which PC gets the value, and at the next edge of the clock the result of this instruction will get stored in the register file. Okay. And at the same time we will arrange, we will see in the next slide that PC will have to get a new value and be ready for the next instruction. So, let us complete that part and see how PC is to be incremented. So, all we need to do is have 4 added to the PC contents and connect the result back to the input of PC. So, this is an adder with one input as 4, one input as PC, and output of this is going back to PC. So, you give, let us say at time t the output of PC was available for a new instruction, and then at time t plus 1, I am counting time in terms of clock cycles, not in nanosecond now. So, at time t plus 1, which is the next clock, you get a trigger here and a trigger there. So, the current instruction completes by storing its value, storing the result in register file, and at the same time PC gets the new value and ready for the next instruction. So, that completes one cycle, and if the next instruction was also of the same type, in the next cycle that instruction will be executed. So, this cycle can go on, and the important thing to note here is that the instruction is executed in one clock cycle. Remember that in past we have talked of CPI and we have talked of figures of CPI which are 2, 3, 4 and so on. So, later on we will discuss design where instruction execution does take multiple cycle, and there are good reasons why we would do that, but currently this design is aimed at doing the instruction in a single cycle, and that was a simple component which I was talking of. We are talking of a simple possible design. Okay. Now, we have seen design for these 5 instructions. We need to now go further. We need to augment this to include more instruction, and we will see that by making small incremental changes, we can accommodate more and more instructions. So, let us address load and store instructions next, and the common thing there is that memory has to be accessed, okay, and the mechanism for calculation of memory address is same. You have to take this number, okay, which is a signed offset 16-bit number, and contents of this register, add the two and apply that as address for the memory, okay. And this field defines the register which will exchange the data with the memory depending upon whether it is load or store, right. So, we need to look at these two registers specified by these two fields and a constant. Okay. So, here is the same design we have done so far, and now we will add more things to it to make it possible to do store instruction. We will then add load instruction. So, first of all we need to bring in data memory, right. Unlike instruction memory, this will have data input as well, and that is actually the only difference. You have address, read port, write port. Okay. Well, actually strictly speaking, this will be considered, it will not be considered a 2-port memory, it will be considered a 1-port memory, because you either do read or write, there is a single address, all right, and we will define control signals which will ensure that either you perform read or write. Okay. So, it is a single port memory, but it can do read or write, whereas this is a 3-port memory, 2 read ports and 1 write port. This one has a single read write port. In fact, some memory modules have these common. Okay. There is the same set of wires which are connected to memory, through which you can send the data in or take the data out. So, it that data terminal is a bidirectional one. Okay. So, there is one address line and a bidirectional data line. In this case, of course, again for simplicity, we have separate read and write lines, but there is a common address line. This is also a single port memory with a single read port, and that is all. Okay. Now, we have positioned the memory here, we now need to connect the inputs and outputs for this. So, first of all, the address, as I mentioned, will be produced by performing an addition. So, we will use ALU for doing the same thing, okay, because load store instructions do not require other arithmetic operations to be performed. We will use this ALU itself to calculate the address. For doing PC+4, we could not use this because we had instructions which were using it for some other purpose, and this PC+4 was being done over and above all that. So, we required a different piece of hardware here, but for load store instruction, we will use ALU to do the address calculation, and therefore, I have connected it in this manner. I need to make sure that the right inputs come to the ALU for calculating address, and that is the next thing. So, we do not directly connect register file output to ALU, because for address calculation it is a constant coming from instruction which will be loaded. So, we need to put a multiplexer here, okay, which will have this RD2 output for R class of instruction, but it will have something coming from this for performing address calculation. So, I have not connected it yet here, because those 16 bits which we get from instruction need to be sign extended before we can pass it on to ALU. So, this is the block which is doing sign extension. It takes 16 bits as input, bit number 0 to 15 of the instruction, and it does sign extension. Okay. So, here it is a 32 bit output. So, wherever I have not labeled things, assume that you have 32 bit output, 32 bit signals. Okay. Each wire is actually carrying 32 bits. Exceptions are here where I have labeled explicitly, or here where I have also indicated that it is 16 bits explicitly. So, now you see what is happening, that RS specified by this field would bring out some 32 bit number here, okay. 16 bit taken from here, sign extended, and we will control the multiplexer to select this path. Okay. When it is load or store, it is this path which will be selected. So, we must give input 1 to the multiplexer, control input 1, and for add subtract instructions we must give 0, so that this goes in. Okay. So, wherever we have actually two paths converging to same destination, you will notice that we put a multiplexer, and then it is responsibility of the controller to control this multiplexer correctly, so that depending upon what we are trying to do, the right thing gets done or right data gets passed through that multiplexer. So, this part takes care of inputs for data memory, the address input in particular. So, it comes from here, and inputs of the adder, inputs of the ALU are also arranged now properly. Okay. To complete the picture, we also have to make sure that the data from register file goes to the data input of this memory. Okay. So, where does it come from? In this diagram, where will the data come from, which will have to be connected to this WD? Yeah, RD2, because it is the RT, the third field which actually specifies which register has to be written. So, that is already happening here actually, and that output is available here. So, we simply need to connect this to this. Okay. So, now there are complete arrangements for performing store word instruction, and now we can move to the load word instruction. Okay. Now, in the load word, the address generation part is same, and that we do not need to touch. Okay. The same mechanism, same paths, and that need not be modified. What additional thing we need to do for load word is to take the data from data memory and put it back in register file at appropriate address. So, first of all, we have this line going to WD, write data of the register file. So, we have broken this here, so that we can take this and put a multiplexer. Okay. So, there are two options now, and they need to be joined with a multiplexer. So, this multiplexer, when you give control as 1, then it will send this to the register file, and when the control is 0, it sends this to the register file. So, we will have to remember that for add, subtract, and or instruction, the control has to be 0, and for load instruction, control has to be 1 here. Okay. So, this is one part of the picture. The second part of the picture is to give the correct write address. Okay. The write address comes from, now let us figure out from where the write address has to come. See, for add subtract instruction, write address is coming from this part, okay, bit number 15 to 11 to 15, and for this it will come from bit number 16 to 20. For load instruction, it is this RT which will be used here. For add subtract, it is the RD which decides the right destination. Now, it is RT which will do it. So, again we need to make changes here, introduce a multiplexer, because it is either bit 11 to 15 which go there, or bit number 16 to 20 which go there. So, we have to make a provision for that. So, we remove this line and put it through a multiplexer, and the two choices are either this or that. This is the choice which will be taken for load instruction, this is the choice which is taken for add, subtract, and or SLT instruction. Okay. So, now we complete this is the complete picture for now 7 instructions we have done: add, subtract, and or SLT, and load, store. Okay. So, everything which is required for these as far as data path is concerned is there. Now, let us look at branch and jump instruction. Again, we will take one by one. They would need to do something with the program counter, because these instructions influence how the next instruction is chosen. We did not modify this part for load store, because this part continues to be same, right. You have one instruction, the next instruction follows, but for branch instruction we need to modify this, and also we will use ALU for equality test. Okay. The comparison will be done, and ALU will produce a bit which will indicate whether the two inputs were equal or unequal. Okay. The branch instruction has this format, opcode. This is I format as we have for load store. RS and RT are the two registers which will be compared, and this number would be added as word offset to PC. Okay, and it will be PC plus 4 to which we will add, because that part we want to retain as common for all the instructions. Okay, so again start from this point where we have come up to. So we need to do some modification here. Instead of sending PC plus 4 back directly to PC, we will introduce more options, and the option would be that this with something added to it. So now let us look carefully. First of all, this is a multiplexer which is making a choice. Either we take PC plus 4, okay, or we take output of this adder which is adding something to PC plus 4. What is it we are adding? We are adding this 16-bit constant which has been sign extended, but it has also been shifted. This S2 I am using to shift this number by 2 bits to the left, okay, which is effectively multiplying by 4 and getting a byte number from word number. So this, as I had discussed earlier, it is a matter of simply wiring things correctly. So we have the correct offset coming here, which gets added to PC plus 4 and is available to this multiplexer. Now this multiplexer has to look at which instruction it is. If it is not a branch instruction, it will simply allow this to go through. If it is branch instruction, then it looks at result of comparison in the ALU, and accordingly a 0 or 1 will be chosen here. So again we will get into those details when we discuss the control. So for the moment we assume that somehow there will be some logic put together which will take care that a correct value 0 1 is given here. So as far as data path is concerned, what we have introduced here essentially is one multiplexer and one adder, and this wiring of signals, so that a shift of 2 bits takes place. Okay. Now just to remind you, we had seen that sign extension and shifting are essentially wiring. There is no active gate or any active component involved. Sign extension means repeating one particular bit, and shifting means just rearranging these and supplying a constant 0 to some of the bits. So in the previous diagram, the sign extension and the shift are essentially these kind of wiring elements. Okay. Now finally we are coming to this jump instruction. Jump instruction has only two fields, the opcode field and a 26-bit field which decides the next address. So once again, since it is not a full 32-bit address, we need to retain some bits of PC as it is. Okay. So what we will do is we will take these 26 bits and 4 bits from PC plus 4 again, not PC, and form a new address for the next instruction. So we would require another multiplexer which will provide one additional choice. So we introduce that multiplexer here, remove this line and pass through a multiplexer, and the input for this multiplexer is coming from instruction bits. We are taking these 26 bits from the instruction field, okay, shift it left by 2 positions to get 28, again same reason, we want to get byte from the word number. 4 bits we are picking from PC plus 4, okay, bit number 28 to 31, and these 4 bits and these 28 bits are concatenated together to form a jump address, which is a 32 bit value, and this is available as yet another input for going back to the program counter. So, program counter PC has 3 possibilities, either plain PC plus 4 or this PC plus 4 plus offset, or this combination of PC bits and instruction bits, right. So, you can actually combine these two multiplexers into a single 3 input multiplexer. That is another way of designing, but we will just retain it in this manner. Okay. Now, the next thing is to start worrying about how we are going to control this data path. Okay. What are the points where we need to apply control signals? So, that is what we will see next. So, all multiplexer would require control, and in this exercise of identifying control, we will assign names for the purpose of reference for all the control signals. So, we will call this control signals for this multiplexer as RDST or register file destination. It will select the destination address in the register file, it comes from here or from here. Then register file needs a control signal to tell it whether it has to write or not. Okay. All instructions you would notice are not writing into register file. So, it is only first 5 instructions write and load instruction. These 6 instructions out of the 9 write into register file. So, this will have to be made 0 or 1 accordingly. ALU source, which I am labeling as A source, is the control signal for this multiplexer, and this will distinguish whether ALU is being used for address calculation or for normal arithmetic logical operations. ALU would require 3 bits to control it. Recall the design of ALU which we had done. We had some circuit, and then at the end there was a 4 input multiplexer, okay, which will select AND output or plus minus output or output for SLT. So, 2 bits are required to control that, and another bit to choose between add subtract. So, there were total of 3 bits. I am labeling that as OP, standing for operation. Then a status output which will come from ALU, I am labeling it as Z, standing for 0. So, it is a comparison of the 2 operands from the point of view of BEQ instruction. So, comparison, you recall, was done by doing subtraction and checking if the result is 0. So, that is why I have labeled it as Z. So, this is not an input, this is an output, this is a status and others are control. Data memory requires control for read or write. So, MR stands for memory read, MW stands for memory write. We will make sure that memory does only one operation at a time. Actually, in this kind of arrangement where read and write lines are separate, it is also possible that you do read and write simultaneously in this, okay, but it has to be from the same address. So, same location in the memory is used for reading and writing simultaneously, but in our design we do not do that. We will either do read or write, okay. And then another multiplexer here which is distinguishing between what goes to register file, whether it is from memory or from ALU, all right. So, memory to register file M2R. This is called P source, PC source basically, either here or there. Then whether it is jump instruction or not, so another control signals. So, these are the control signals. So, we require some circuit which will produce so many outputs. So, 1, 2, 3 plus 3 6, 7, 8, 9, 10, 11. These 11 outputs, and that control will have to look at this and also look at two fields of the instruction, okay, the opcode field and the function field. So that is the controller which needs to be designed. It has to have these 12 inputs, in fact strictly speaking plus 1, 13 inputs and 11 outputs. Okay. So, if you can design that and plug it in here, that will complete the task, but we will not design it as a monolithic circuit. We will design it again in terms of some simpler parts, as you will see now. So, now we want to bring in the controller. We will not go into details, but we will just go through an outline of what it is going to be. First of all, we look at the opcode bits, and these bits are sufficient to distinguish between jump, branch, load, store, and this group of add, subtract, etc. altogether. Okay. So, except for controlling ALU, from these 6 bits we can derive all the information. So, out of the 11 signals, 8 can be straight away figured out using these. Of course, generating this will require us to look at Z also, right. So, let us connect the output of this control. I will show the outputs and connect to various signals which can be driven by this. So, if it is load instruction, which we can figure out from here, we will allow this to pass through here, otherwise we will allow this to pass through. So, this R dash can be determined from this. Whether we have to write register file or not can be determined from this. ALU source can be selected, okay, it can be determined from this. Memory write and memory read. Okay. So, if it is load instruction, we will do memory read. If it is store instruction, we will do memory write. Okay. Then control of this multiplexer. Okay, it has to distinguish between load from other instructions. So, that also can be done. Here we are doing slightly differently. We are first of all figuring out that it is a branch instruction. Okay. So, this controller will activate a signal which tells us that it is a branch instruction, and that we AND with the Z output to control this P source. So, you can see what is happening. If the instruction is not a branch instruction, you will have a 0 here, okay, which means that P source is 0 irrespective of what is Z, and the multiplexer passes the upper input. So, when it is not a branch instruction, we do not branch, we do not even look at Z. When it is a branch instruction, we will have this as 1. Okay. Controller will make this output as 1. Now, it will depend upon Z, we will get a 1 here or a 0 here. So, if the result of comparison was true, okay, if the 2 registers were equal, this will be activated, this will be 1 and you will get a 1 here. So, this address will go as the next address of PC, next value of PC, and if the test failed, then this will be 0, you will have a 0 and PC plus 4 will continue, right. Another way, if you recall the gross diagram I had drawn where there was a data path and controller, I had shown status signals going to the controller. So, if strictly speaking controller is not just this, it is this plus this, okay. But for it actually simplifies the matter to look at it as a 6 input circuit rather than a 7 input circuit, because the influence of this has been handled separately, which makes it somewhat convenient. Then we can also control this multiplexer by figuring out whether it is a jump instruction or not. So, now what is left is this opcode, the operation which ALU has to perform, and it will depend upon 6 bits which come from the function field. Okay. So, instruction 0 to 5 would be seen by another kind of control circuit. I am calling it A control or ALU control. So, looking at these 6 bits, we are trying to determine what these 3 bits are. But remember that ALU is being used for load store instructions also for a different purpose. So, we need to look at this also, but we don't need to feed all those 6 bits here. What we need to tell this circuit is which class of instruction it is, okay, whether it is R class, one of those instructions, or it is load store or something else. So, we will have some information coming out from here connecting to this, and this needs to be just 2-bit information, because we like to distinguish between 3 different cases. The R class instruction, add, subtract, and, or, and SLT, that is one possibility. Load store together grouped as another possibility, and all the rest as third possibility. So, we will take 2 bits out of this and connect to this, okay, and I am calling it OPC, which stands for operation class. So, basically this circuit now has 6 inputs plus 2 input, 8 inputs, and producing 3 outputs. So, we have taken special care to keep the number of inputs low. So, the complexity of a combination circuit like this or like that depends upon the number of input lines and number of output lines, but I will not explain that, but you can take it that with the number of input lines, the size of circuit or the complexity grows generally exponentially, okay, but with outputs it will generally grow linearly. So, we are more worried about keeping the number of inputs as low as possible, okay. So, if there are large number of inputs, then we can look at parts of it separately and then combine the result. That is always a better strategy, and that is what we have followed. So, this circuit is predominantly looking at the opcode field, whereas this is predominantly looking at the function field, and some additional information it requires about opcode is being actually processed by this and made available here, right. So, after having done this, what remains is basically to look at design of this and design of this. So, if you can enumerate what outputs you require for what inputs, you can do it in a straightforward manner, and same thing here. So, we will take it up in the next class. So, just to summarize, we have designed a processor except for some controller details for these 9 instructions: add, subtract, and, or, SLT, load word, store word, BEQ, and J. And our approach was very simple step by step approach. We gradually put the components on the table, connect wires, and build up the circuit. So, first we took this group of first 5 instructions which are similar in nature, okay. The only difference comes in the way you control the ALU. So, we did that. We started with these 5, added store and load, and then added BEQ and jump. Then we identified the control signals for the various components which were put there, and we placed some black boxes which we called controllers, which are expected to produce these signals. And the next task will be to look at details of these 2 black boxes and design these. That is all for today. Thank you.